So in this video, we're going to be looking at infrared spectroscopy and how we can use infrared, otherwise known as IR spectroscopy, to actually find the functional group present within a particular compound of an unknown sample itself. Now, to begin with, right, what actually happens in infrared spectroscopy is we place our sample on something called an infrared spectrometer, and a beam of infrared radiation is actually passed through our sample of the chemical itself. And what happens is the bonds within our actual chemical between different atoms absorb different frequencies of infrared radiation. And so by doing this causes the covalent bonds within the molecule to vibrate more. Now, we don't need to know much about the vibrations in A-level chemistry for OCR A, but at degree level, what actually happens is the infrared radiation causes the covalent bonds to actually bend and stretch. Now, when we look at infrared radiation, right, our sample actually absorbs different frequencies of infrared radiation, and anything that's not absorbed is passed through to reach the detector, where we end up with something called an infrared spectrum, which looks something like this, where we have on our x-axis the wave number measured to the centimeter minus 1, and then we also have transmittance or percentage transmittance on our y-axis, which you can see like this as well. Now, let's say if I were to conduct infrared radiation on, let's say, a vacuum, a blank sample of nothing, what I would actually end up with is a straight line, because we've got no molecules to absorb any of that infrared radiation itself. We've got a vacuum, the absence of matter itself, right? But what if I were to have a sample, right? What would actually happen is that the infrared radiation will be passed through our sample. The sample absorbs different frequencies of infrared radiation, causing the covalent bonds to vibrate more, and so the infrared radiation that's not absorbed is detected by a detector, and we end up seeing something like this. And what we can actually do is we can look at particular peaks or particular parts of absorption, and that actually represents a certain bond being present itself as well. Now, there's three characteristic bonds that you need to be aware of and how they actually relate to certain compounds, especially when it comes to alcohols, aldehydes and ketones, as well as carboxylic acids as well. Now, the first peak is going to be for your alcohols or your phenols as well, and that's going to be around the 3,200 centimeters to the minus 1 region, where you expect to see absorption right within this region itself. And normally, right, this actually indicates the presence of an alcohol. So in this case, right, let's say if I were to deal with the alcohol, which is going to be ethanol, I know it's going to be ethanol because we've got a peak around about 3,200 centimeters to the minus 1. Now, you can actually quote this from your data sheet, where you can say that it's going to be an absorption between 3,200 to 3,600 centimeters to the minus 1 itself. That indicates the presence of an OH bond and therefore an alcohol itself. So again, let's say if I had something like ethanol, which is going to look like this, we know this is going to be ethanol because it contains that characteristic OH bond for an alcohol itself. Or about if I were to look at aldehydes and ketones, let's say if I had propanone in this case, or even let's say if I were to have propanol in this case, right, what I would expect to see is a characteristic peak for the carbon-oxygen double bond, and we expect to see a sharp pointy peak, right, around about the 1,700 centimeters to the minus 1 region. To quote it exactly from the data sheet which you're given in the exam, it's going to be between 1,630 to 1,820 centimeters to the minus 1. And so you can see this characteristic peak over here itself, right? Now, what about carboxylic acid? We know there's two characteristic bonds in here that define this has been a carboxylic acid. I've got the carbon-oxygen double bond, and then I've also got the OH bond, but this time it's a part of the carboxylic acid functional group itself. Now, the easiest part of this is to say that the peak around 1,700 actually indicates the presence of a carbon-oxygen double bond, because we've got a peak quoted from our data sheet between 1,630 to 1,820 centimeters to the minus 1, and that shows us that we've got a carbon-oxygen double bond. But how do we prove that this is a carboxylic acid and not an aldehyde or a ketone? How is this going to be butanoic acid and not butanol or butantuol? Well, what we can actually do is look for another peak, which this time is going to be for a carboxylic acid OH rather than a actual alcohol OH, and so we expect to find a value, right, that is going to be more shifted towards the right for the OH, and it's going to be between 2,500 and 3,300 centimeters to the minus 1 as well. And so in that case, right, if we've got that, we've got OH, but this time for a carboxylic acid, we've got an OH bond for that as well. So yeah, in that case, you should be able to identify these characteristic peaks quite swiftly in the exam and be able to answer longer, structured analytical chemistry questions with this as well. So yeah, moving on, I've got an example for you to actually try. Feel free to pause the video and have a go. So yeah, student conducts IR spectroscopy on a sample which could contain either of the following compounds. Ethanol, we know that's got a characteristic OH bond over here because it's an alcohol. Propanoic acid is going to have an OH bond, but it's going to have a different absorption because it's a carboxylic acid. And then we've also got a carbon-oxygen double bond there. Cyclohexanone, right, will have that characteristic carbon-oxygen double bond, and that will happen whether we've got an aldehyde or a ketone itself as well. Now we're asked to use the IR spectrum and to deduce which compound is present within the sample. Now straight away I can see that I've actually got a peak for an OH bond over here, and I can also see that I don't have a peak for a carboxylic acid OH bond or for a carbon oxygen double bond as well. So I know this is going to be ethanol. How do I actually word that in the exam? Well, I tell the examiner in layman's terms, quoting values from my data sheet, that there is a peak for an OH bond, in brackets alcohol, present between 3,200 to 3,600 centimeters to the -1. I could also use the word absorption rather than peak as well. And so we know that this compound is going to be an alcohol, right? Which of my three options I've got above there is going to be an alcohol? Well, we know it's going to be ethanol, so the answer is going to be ethanol. So we can further show that this is going to be ethanol and not propanoic acid or cyclohexanone by looking at the absence of the other two peaks. So there's no sharp peak present for a carbon-oxygen double bond between 1630 to 1820 centimeters to the -1. So the compound does not actually contain a carbon-oxygen double bond itself. There's no broad peak present for an OH bond for a carboxylic acid between 2,500 to 3,300 centimeters to the -1. So the compound is not going to be a carboxylic acid itself. And then we can actually list and say what our compound is going to be. And for extra marks, what I would recommend that you do is when you deal with these spectra, like let's say this one over here, I would actually draw a box around this and I would annotate this and say what peak we've got. So we've got a peak between 3,200 centimeters to the -1 to 3,600 centimeters to the -1, and that's going to show us that we've got a OH for an alcohol being present as well, because that sometimes can actually get you some marks as well, just in case you forget to mention some things as well. So yeah, moving on, feel free to pause the video and have a go at the following. So yeah, in this case, right, we can see that a student conducts IR spectroscopy on a sample which could contain either of the following compounds. Again, we've got ethanol, propanoic acid and cyclohexanone. Now straight away I know the answer is going to be cyclohexanone. The reason why is because I've got a sharp peak over here that indicates the presence of a carbon oxygen double bond, but I don't actually have an OH for a alcohol, which I'd expect to see over here, or a very broad peak around this region over here for a carboxylic acid OH itself. Well, how do I actually word that in the exam? Well, I say there is no peak for an OH bond for an alcohol present between 3,200 to 3,600 centimeters to the -1. So I know the compound is not an alcohol. There is a sharp peak present for a carbon-oxygen double bond between 1630 to 1820 centimeters to the -1. So the compound does contain a carbon-oxygen double bond. But then how do I know that it's not carboxylic acid? Because carboxylic acids have that peak as well. Well, we see there's no broad peak present for an OH bond for a carboxylic acid between 2,500 to 3,300 centimeters to the -1. So the compound is not going to be a carboxylic acid itself, and what it's going to be is cyclohexanone. And again, you can label this peak over here by drawing a box around it or something like that, and then you can quote the value, draw a little arrow, and say you've got a peak between 1630 centimeters to the -1 to 1820 centimeters to the -1 for a carbon oxygen double bond itself as well. Now I've got another example, the final one. Feel free to pause the video and have a go. So yeah, it's the same thing again over here, right? We've got an IR spectrum, and what we need to be able to see is that we've got a carboxylic acid straight away from this characteristic carbon oxygen double bond peak, as well as this carboxylic acid OH peak itself. It should really be shifted more towards the right, but that's very broad, and you can see, right, that it spans, right, quite a long range as we expect it to do. An alcohol, we'd expect it to be a bit more sharper and a bit more pointier compared to our carboxylic acid OH itself. So we know it's going to be propanoic acid. How do we explain that to the examiner? Well, we need to say the following, that there is no peak for an OH bond, an alcohol present between 3,200 to 3,600 centimeters to the -1. So the compound is not going to be an alcohol. There is a sharp peak present for a carbon oxygen double bond between 1630 to 1820 centimeters to the -1. So the compound does actually contain a carbon oxygen double bond. So at this moment in time, it could be an aldehyde, could be a ketone, but it's not going to be an aldehyde or a ketone. It's going to be a carboxylic acid, Why is that the case? Because there is a broad peak present for an OH bond between 2,500 to 3,300 centimeters to the -1. So the compound is going to be a carboxylic acid, and so it's going to be propanoic acid itself. So again, I can actually label my peaks over here. So I've got here a carboxylic acid, which you can see, right, we've got that broad peak over there. And all I'm going to do is I'm going to annotate it and say we've got a peak, right, between 2,500 centimeters to the -1 to 3,300 centimeters to the -1, showing that we've got an OH for a carboxylic acid. And you need to specify that it's a carboxylic acid. And then we also need to show, right, this peak over here. We need to be able to annotate this peak and say that we've got a peak between the region of 1630 to let's say 1820 centimeters to the -1. So we know we've got a carbon oxygen double bond being present there as well. Now that's how we answer these questions when it comes to infrared spectroscopy itself. Now moving on then, right, there's some facts that we need to be able to recall when it comes to infrared spectroscopy, but then at the same time we need to know about how infrared radiation links to global warming itself. Now let's say if I were to take the Earth, right, and the Earth is surrounded by something called the atmosphere, and in that atmosphere there's something called the troposphere, which is a layer in there. Right, this layer actually contains gases such as carbon dioxide, methane, and water vapor. Now, what scientists have done is they've made a link between these gases, right, and how our planet is actually heated and kept warm as well. Now, when we look at the sun emits infrared radiation, and what happens is that the troposphere, these gases in the troposphere, actually absorb some of that radiation, and they re-emit it in all directions, including outer space and including to the Earth as well. And let's say if it hits the Earth, right, the Earth is going to absorb some of it, and then it's going to re-emit it back in all directions as well. And one of the places where that radiation is now going to reach is going to be the atmosphere again, which does the same thing, where it re-emits it in all directions, including space, but then some of it's re-emitted back to the Earth itself as well. Now, carbon dioxide, water vapor, and methane gas have all three been linked to this effect. And the reason why this actually happens is because they contain characteristic OH, carbon oxygen double bonds, as well as CH bonds, and that's something that we have to be able to recall as well. Now there's two different uses of infrared spectroscopy that you've got to know about. One of them is going to be in the use of modern breathalyzers, where we use infrared spectroscopy to look for the presence of ethanol, right, within a driver's breath. And the reason why this actually works is because it actually detects the OH bonds present within ethanol itself. Now another thing that we actually use it for is monitoring gases causing air pollution. We use it to monitor concentrations of polluting gases in the atmosphere, such as carbon monoxide or nitrogen monoxide, and the intensity of the peaks that we actually get correspond to the carbon monoxide and nitrogen monoxide bonds actually studied as well.